welcome everyone to the very last lecture where we're going to talk about approximation algorithms. Before that, obviously the final is Wednesday. If you haven't seen, I wrote a giant thing on Piazza about what to expect on the final. Homework 6 is due tomorrow. It should be a good review for what's going to be on the exam, so try to get that done. If you need more time on it, let me know. It's not super important that it's due tomorrow, other than I don't want you worrying about it before the exam. But if anyone needs more time, let me know. And then I'm also going to, so I was originally going to have a Zoom lecture to make up for the very first Wednesday that we skipped, but I don't think anyone's going to watch it because it's stuff you're not going to be tested on. So instead, I'm just going to make review videos. So I'll go back to things like divide and conquer, not DP because we did every DP problem in existence already, but some of the older stuff, and I'll make extra videos to help you review those topics if you're interested. So that's my plan instead of having that last Zoom lecture. So any questions before we get started? Yes.
So when all the theorems that are covered in the lecture or any videos are fairly true?
Yeah. So anything that I've covered in a video, in the book, or in lecture, you can use on the final exam and say a graph reduction. So the main example is longest path. So I didn't cover longest path in lecture, but I did cover it in the videos, and it's also in the book. And so, for example, for homework 5, you were allowed to use longest path to solve problem 1. And similarly, there's a bunch of algorithms in the book that, I covered most of them, but there's here and there's things in the book or there's things in the video that weren't covered in lecture, and you can always cite those. Just be I'm using this algorithm from a video or from the book or something. So those are all, you can use those. Of course, you should be using the Max-Fomin cut theorem. Pro tip, please use that. It's super useful. If you watch the videos on max flows, I used it in every single problem because it's very useful. So please get comfortable with that theorem because it's so incredibly useful. You'll use it all the time. Yes?
So for some, the lemmas that are covered in the videos, those have to be true.
If it's in a video, you can use it, but
Well, if it's lemma,
typically the lemmas are things I made up to prove a specific algorithm, so it probably won't be directly applicable. But if you can find a way to use them, you're free to use them.
okay.
Just make sure you're citing hey, this is from a video on graph reductions or something. Yeah. Yes?
Are we assumed to be using Orleans every time we use the min-flow max cut theorem?
Absolutely not. So you're either using Orleans or Ford-Fulkerson. Typically, you're using Ford-Fulkerson for the problems I'm giving you, just because they usually have a bounded flow value, and so you should be using Ford-Fulkerson. Usually it doesn't matter. So for example, on homework 5, if you used Orleans, you're doing just as well as if you use Ford-Fulkerson, so there's no difference in runtime. But in general, there could be a problem where the flow value is actually super small, in which case Orleans is a horrible mistake. But I doubt that'll happen. It didn't happen in any of the homework problems. It's not going to happen on the exam. But just general advice, that's not true. But yeah, for purposes of this course, you can basically always use Orleans, but people prefer Ford-Fulkerson usually. Other questions? Oh yeah, one other thing. So the discussion tomorrow and Rahul's office hours, that 3-hour window, is going to be review. I'm also going to be doing a review either today or tomorrow. I don't know yet because I have 5 hours of research meetings after the class today, so it depends if I'm still alive after that. But if I'm not alive after that, it'll be tomorrow at like noon. I'll keep you guys posted. But you'll have plenty of time to review stuff. And then obviously I have office hours after this. This lecture is probably going to go shorter than usual, so we'll have time to review too. So, yes. No. So, like just like whatever you guys want to talk about, we can review the most recent topics. Yeah. These review videos specifically are going to be about, honestly, it's going to be half the stuff that won't be on the exam and half the stuff that will be, because it's just going to be everything in the course. And I'm also going to put out way more videos on reductions. If you haven't seen yet, I put a video on reductions for the partition problem, and it's 40 minutes long. You don't need 40 minutes to solve that problem. It's super easy, but I went through like every single step and every possible question you could have. So if you really want a very thorough, detailed understanding of reductions, definitely watch that video in depth. If you're already comfy with reductions, you could probably skip to the middle or triple speed it. But that video, I went in excruciating depth on what to do. So if you're kind of fuzzy on how reductions work or NP hardness, in that video, I go through it in a lot of detail, including my problem-solving process. Like I walk you through how you might even generate a reduction and based on the problem, how to even try to attack it. So it's got everything you'd possibly want in there. But we'll go through more NP hardness reductions today as well. So I think so, yeah. Yeah, that one's partition. And then 11B is about the graph, vertex cover, max cliques, those things. But 11A, I go through in excruciating detail every single step of the process, so you get the full sense of what to do. And honestly, 11A is it's more detailed than you need. So on an exam, I'm not expecting you to go through every step I did. It's just to help you get a better understanding. 11B is a better representation of what we'd expect for you on an exam, like the level of detail. Any other questions? Of course, if you have other questions, you can also ask in office hours later. Yes? Mm-hmm. For homework 5, there's no proof yet. For homework 6, there is.
So you need proofs for NP hard problems, but not non-NP hard problems?
You need proofs for NP hard problems and flow reductions, specifically. General graph reductions, you usually don't need to because it's like a direct reduction, right? You make the new graph and you do a shortest path, and it's obviously exactly the problem you want to solve, so you don't really have to prove anything. In general, depending on how complicated the reduction is, you do have to, I won't say prove it, but you should explain why the problems are equivalent. For flow reduction specifically, it's generally less clear, and that's why you need a formal proof, like we did in class, where you have, if I had this flow of value n, then I have n disjoint paths, and you prove both ways. So for flows, it's generally different. For homework 5, you didn't have to prove them, though.
Because the last question on homework 5.
Yeah. Yeah, it's an assignment problem.
So
Yeah.
for that, we don't have to prove it?
In general, yes. For homework 5, you didn't, just because it's pretty obvious, the correlations there. And, it was your first time doing that stuff, so I didn't want to make you, also throw a proof in. But in general, in the future, you would have to prove that thing. Yeah. Yep. They're not going to be complicated, right? For the add problem, I put the solutions are up now. And in the add problem, it's basically if you had a valid assignment of adds, then you're going to send a unit of flow down the path from the ad agency to that demographic to that person. And on the converse, if there was a path in the flow from an ad agency to a demographic to a person, then that's going to be your assignment of an ad to a person for the website thing. So it's really straightforward to prove it. Yeah.
Like, I can just write out words. Like, it doesn't have to be like a concrete mathematical, like, oh, whatever edges, like, something.
You're kind of baking that in implicitly. I can go through the solution to kind of give you more ideas of what's expected in office hours if you want. But there's some kind of nice in-between. There's an in-between, like, saying just words and saying rigorous, like, look at every edge and stuff. There's a nice, like, middle ground that I kind of put in the solutions. That's usually what you're shooting for.
Because, like, I was looking at, like, the exponents of the computer videos, like,
Mm-hmm.
like, for the algorithms, like, okay, like, I feel like I would be able to, like, make those, but then for, like, the proof part, I was like, I don't think I'd be able to, like, write all that out. Like, I could, like, kind of, like, explain why they're equal.
Yeah.
Like, words kind of, but, like, mathematically, it was, like,
Yeah.
if I had, like, 30 minutes for a problem, like, I don't think I'd be able to, like, come up with the full, like, proof. So,
Mm-hmm. Yeah, we can discuss that in office hours, kind of how to do those proofs in an intuitive way that's like almost mechanical. All right, so let's get started. So approximation algorithms, what even is this? So in last lecture, we talked about NP hardness, and the intuition here was if a problem is NP hard, then we don't think there could exist a efficient solution to that problem. And to kind of give you an example of why this is bad is if a problem has an exponential time, like let's say 2 to the n is the best runtime for some problem. And let's say it's a really small problem. So let's say you're looking at a graph, you want to find some thing in the graph. And just think of like the Facebook graph, like all the people that are connected in that graph. Well, n is like 1 billion people, but even for 100 people, 2 to the 100 I think is bigger than the number of atoms in the known universe. That's the buzz phrase they always like to say. And that's kind of crazy, right? So even for a tiny little graph, basically the graph of connections in just this course, it would take you billions of years to actually solve that problem with a computer. And just imagine if you tried to solve that problem on an actual real-world graph with 1 billion people in it. So this is the issue with NP-hard problems. Realistically, you're not going to solve them. It's not going to happen. So that's why we care about NP hardness. It tells us that a lot of these problems that are important and we care about, we just can't solve them. But does that mean we give up? No, we don't give up. So what do? Well, we turn to approximation theory. And so what's approximation theory? It just says we're going to trade off accuracy for runtime. So now I don't need an optimal solution. So don't give me something optimal. Just give me it fast. And I hope you can see why I left this to the last lecture, not just because they're harder, but also because this is like the opposite of what I've been teaching you so far. Normally, you want to make something correct, so it is optimal, and then worry later about improving it to make it fast. But this is basically the opposite. You don't care if it works, you just want it to be fast. So that's basically the idea. Instead of giving me something optimal, give me something that's good. Like, we still don't want it to be really off, but make sure you can compute it fast. So something polytime. So that's the main idea. So of course, we need a formal framework for this. So we're going to consider optimization problems. So I'm going to let opt of x denote the optimal solution value for a specific input instance to the problem. So this problem could be something like min vertex cover, max independent set. It could be the file sorting problem, just any kind of optimization problem we want to solve. And then we'll let A of x, this denotes some algorithm that we've created to solve the problem. And now we're going to say that A is an alpha of n approximation algorithm if and only if either the optimal divided by the algorithm's value is at most alpha of n, and this is specifically for a maximization problem. For a minimization problem, we want the algorithm's value over the optimal to be at most alpha of n. So to give you a simple example of this, let's say we wanted to solve the vertex cover problem. And let's say I gave you a vertex cover of size 10 for the problem, but the actual minimum vertex cover, the best we could have done, the opt for that instance, was size 5. So since this is a minimization problem, the value we computed was more than the best we could have done. So it's not exactly accurate, but it's not too far off. So in this case, our approximation factor is just the ratio of what we computed, the quality of our solution. So you could think of this as the quality of our solution. And this ratio is 2. So our algorithm, if this still was true for every possible instance, would be a 2 approximation. So the way you want to think of this is the solution we create is never more than a factor of 2 worse than optimal. That's what it means to be a 2 approximation. So in general, you might be thinking, okay, why are we looking at ratios, right? So if I wanted to solve the maximize my profit if I'm a company, and the optimal solution is $1 billion, and I gave you $500 million, I've just lost $500 million. That's kind of brutal. So for like profit maximization, let's say the optimal was 1 billion and your AL gave me $500 million. Then on one hand, I would say this is a really good algorithm. It's a 2 approximation. So alg is a 2 approximation, right? Because we get half of the best we could have done. We're looking at a maximization problem here. So remember, for maximization problems, we're looking at how big the optimal was and dividing by how big we did was. So it's 1/2 over 1, which is 1/2. And so it's called a 2 approx, but we can just call it a 1/2 approx because that's a little clearer. So we get a 1/2 approx here, which is pretty good. But really, you've lost $500 million. And that's pretty huge. So a common critique of approximation algorithms is because we typically look at what's called multiplicative approximation, which is saying, look at the ratio of the solutions. And the justification here is, although you could view it as we've lost $1/2 billion, which is pretty bad, still $1/2 billion is better than $0, and it's pretty close to $1 billion. It's much closer to $1 billion than, say, $100 is. So still, 1/2 bill closer to one bill than, say, $100 would be. So generally, this is kind of the justification of why it's okay to look at multiplicative factors. Even though you are losing a lot of just raw money here, relative to how much you still get, it's not a huge difference. If you had $1 and instead you lost it and found 50 cents, there's not a huge difference in your buying power, right? There's not a lot more you can buy with $1 billion than you can $500 million. If you have $500 million, you probably can buy anything you want anyway. The extra half isn't really helping you. So that's why we focus on ratios. It's basically good enough, and it's going to be mathematically much easier to analyze. There's still a theory of additive approximation where you consider, like, oh, it's opt minus something, and that's its own theory. But we're going to focus on this multiplicative theory. So any questions on the idea of what an approximation looks like? So intuitively, it's just an algorithm that's not giving you the optimal amount, but it's always close to it. It's always a factor. A of x is always at most opt of x times that number alpha. So you're not exactly opt, but you're pretty close. But the key property is, the benefit is A is probably polytime. You're trading off the accuracy, or how close you are to the optimal solution, for faster runtimes. And usually it's not trivial. I'm talking you go from exponential time to linear time just for a slight inaccuracy. So it's usually worth it. This gives us huge time savings. In particular for NP-hard problems. So you can use approximation algorithms for any problem and make it faster, but it's gigantic when you're looking at an NP-hard problem, because you're going from an algorithm that's probably exponential time down to something even linear. So it's just a massive improvement. You go from 2 to the 100, which would take all of time, versus 100, which would take, you can't even quantify how fast a computer would solve it, because it's like instantaneously, basically. So for a computer, this would, like for n equals 100, a computer is instant for one and never ending for the other one. So I would say that's pretty much worth it. You know, I get half of a solution, but it runs so incredibly quickly that I don't really care. And sometimes you get lucky and you can get arbitrary accuracy. So sometimes you can get something like a 1 plus epsilon approximation. And if you can, this means you can, pick epsilon to get whatever accuracy you want. So usually these are really nice because it directly shows you the trade-off between the accuracy and the runtime. So maybe it's a 1 plus epsilon approx, and it runs in time n to the 1 over epsilon. So obviously, as you make epsilon smaller, your runtime is going to go up in that way. And these things are called polynomial time approximation schemes. And we'll look at that more later. So any questions on the general framework, what the idea is? Yes.
Dependent on n, right?
Yep.
It comes out in fact with different n.
Right. So it depends on n generally. So you could have like alpha n is equal to n. But if you're lucky, it'll be constant. So we'll see mostly examples today of where it's constant. It's always 2 or something.
But if we are calculating that, like, for specific value of n, how do we reduce that?
We'll see an example. So let's see an example right now. So let's again revisit the vertex cover problem. So we've seen this problem in pretty much every context you could imagine. So we've already shown that vertex cover is easy in the case of bipartite graphs. So for bipartite graphs, you might remember there's the video that says the size of a min vertex cover is equal to the size of a max matching. And so we know how to solve max matching efficiently by reduction to max flow, and so we can also solve min vertex cover efficiently using that same algorithm. So for bipartite graphs, we know how to solve it exactly, but we also know for general graphs, it's NP-hard. So it's kind of weird, right? We have this huge gap between bipartite graphs, which are really efficient to solve, and then general graphs where it's impossible to solve. So we probably expect that, there's a way to improve this somehow. There's some middle ground between the two. And that's going to be the approximation algorithm. So why is this problem NP-hard? Well, remember, we reduce it from independent set. So in the videos and also in the book, you take your maximum independent set and you just look at everything else in the graph, and that's a vertex cover. So I won't go through that again, but for the other examples, I'll go through the full proofs. So the reduction was we take our graph G and a number K, and we just output the same graph G and N minus K, or V minus K, depending on which notation you prefer. That's the entire reduction. So now let's try to solve it. So how can we solve min vertex cover fast? So I don't care if it's right, I just want it to be fast. Any ideas? Particularly, you want to focus on greedy ideas. So just what's the first thing that comes to your mind? I bet most of you will think about the exact. Yep, instantly, yes. See, everyone is great at making greedy algorithms. Proving them, though, way harder. So yeah, so what we could do, pick the max degree, vertex in the graph, add it to your vertex cover, remove that vertex. So let me call this V, and then we remove it. This is now G minus V. So this removes V and all the edges touching V. So we remove it to get G minus V, which is G prime, and then recurse on G prime. So this is how we're going to build our vertex cover. So what's the idea here? Well, remember, a vertex cover is a set of nodes that touches every edge. So if we take the node that touches the most edges, that sounds like we're going to get a very small set of nodes. If we're always picking a set of nodes where each node has a ton of edges touching it, we're covering things quickly. Or at least that's how I'm thinking about it. So the idea is we're always picking nodes touching lots of edges. So should need very few of them to touch all edges. Does everyone agree with this idea? Does anyone have a different greedy idea? That's not greedy.
Well, like reference search to like just find out, what the most edges that's starting from that node, and you just keep on removing everything, which is constant.
So it's basically the same thing. You're just going to follow a path while you do it. Yeah, so that will actually be the same algorithm. You're just picking them in a different order. They'll be the same algorithm, though. Okay, so this is basically the main greedy algorithm. So just to summarize in pseudocode, we start with our cover being empty while G still has edges left. So while it's not a vertex cover, we're going to pick the vertex V with the max degree, so it's touching the most edges. We're going to remove that node and all of its edges from the graph, update our cover, and recurse. You just keep doing it until there's no more edges. So at the end, when there's no more edges, that means every vertex we picked has to be touching some of the edges. So the reason it's correct, it's still a vertex cover, is because for any edge, U, V, and G, it has to be covered because at some point, let's say it wasn't covered, well then G still has an edge left. So at that point, we pick V of max degree. In particular, it'll have degree at least 1 because something is touching this edge. And then we'll just, so at that point, either U or V would be added to C, and so C is a valid vertex cover. So no edge can escape our cover because if any edge hypothetically escaped, then neither of its nodes are in the set, and so we did not delete that edge from the graph. And so when we get to the while loop, it'll still say there's an edge left, and then eventually we'll find one of its endpoints to remove. That's the formal proof of why it's correct. It's still a vertex cover, right? We just want it to be not optimal. It still should be a solution. If you gave me something that's not a vertex cover at all, well, that's just completely useless. Like, I don't care if it's small. You could give me a single node, right? One node is super small, but it's not even close to a vertex cover, so it's useless. So just one important point is approximation algorithms still give you feasible solutions. They're just not optimal. Okay, so how good is this algorithm? Well, this greedy algorithm is going to be a log n approximation. So this one does grow with n. Generally, things that grow with n and the approximation ratio, pretty bad. We usually don't really like those algorithms because it says, as you give me more input data, my solution gets worse and worse over time. So as more people join Facebook, my approximation for the connectivity is going to be worse and worse. And that's the opposite of what we want. We want our algorithms to scale to more and more data, especially in the modern era where big data is like the trend. So ideally, we don't want this to depend on n. So this says, as we add more nodes, the quality of the solution gets worse. And this is bad. Okay, so how can we improve this? Oh, okay, yes. Oh, yes, yes. So this specific algorithm is a log n approximation. So the size of the vertex cover is at most log n more than the size of the best one. So this specific algorithm is always at most the best you could have done for the same graph times an extra factor of log n. In particular, this is the size, the number of vertices in the cover. So as you make your graph bigger and bigger, the algorithm needs progressively more and more extra nodes than the optimal would.
Okay, but it's still smaller than alpha and 2 times n. So.
Yeah, it's better than 2 to the n. Yeah, for sure. A 2 to the n approximation algorithm is completely worthless because then you might as well just solve it directly. A 2 to the n approximation algorithm is basically saying it's nowhere close to optimal, it's just trivial.
Or like 2 times n, because I thought you mentioned that like
Oh yeah, linear?
the alpha has to be at most 2 for it to be.
No, there exists a algorithm. That was just an example. Like for this specific example, this is a 2 approximation because the algorithm had 10 vertices, but the optimal had 5.
Oh,
This is not necessarily an actual algorithm for vertex cover. This was just an example.
okay, so it doesn't have, the alpha doesn't have to be smaller.
Nope. Alpha can be any number. It's a function of n. It could be 10 to the 10 to the 10 to the n. It could be n over 2. It could be 1 over n, which would be awesome.
And then there's no max value of an.
Nope. An could be really bad.
Okay.
Yeah. Our goal is to guarantee it's small. That's our goal.
And alpha is the comparison between the set of the solution, not the running times.
Correct.
Or can we also say that it's also the ratio of the running times?
You can also do that, but that's not standard. We're just focusing on the quality of the solutions. Yeah, so clearly, what's the complexity of this algorithm? It's going to be O of n plus m, technically, because we're deleting edges. So this is a linear time algorithm in terms of the input graph. So it's super fast, but it's not really, I mean, it's better than nothing for sure, but it's not that close to the optimal. So we want something else that's fast, maybe also linear time, but has a better approximation factor. So we want to make this number right here smaller. Now remember, we have this neat property that says the min vertex cover is equal to the max matching, kind of like the Max-Flow min-cut theorem. That's what duality means. So duality is saying that the min vertex cover is equal to the size of a max matching in a bipartite graph. But maybe you remember from the video, we actually proved something stronger. For any graph, the size of the min vertex cover is at least the size of a max matching. That's always true for any graph. This is called weak duality. So this is a really special property that not all problems have. Whenever a problem has duality, that usually is a very powerful tool to make the algorithms work better. So just like for Max-Flow is a really complicated problem, honestly. And so is min-cut, but you have this duality, strong duality, that says the optimal solutions for both are equal. And because of that, we were able to come up with efficient algorithms. Well, I guess we didn't, but people have created efficient algorithms for the problem. So whenever you have this duality for a problem, that's giving you a strong indication that you could probably solve it efficiently if you exploit that property. So we also saw in the videos, for Menger's theorem, you can solve the problem of breaking a graph into 2 pieces by deleting nodes. that is equivalent to finding no disjoint paths. And that's what was able to give us an efficient algorithm for that problem. So every time we have duality, we can probably make things efficient. So what could we maybe do here? We know there's this relationship between vertex covers and matchings. How can we use that? And just to remind you why this is true, let's just look at a bipartite graph. And let's pick some matching. Well, what do we know about this matching? So by definition of a vertex cover, we need each of these edges to be touching one of the nodes. And because it's a matching, we know each of these edges don't share an endpoint. And so if they don't share an endpoint, we have to separately pick at least one node touching any matching edge to put in the cover. So for example, what I have highlighted there would be a vertex cover for a bipartite graph. However, let's make it not bipartite, add some other edges. So now, it's true that the min vertex cover is at least that. So here's a maximum matching. But now we have to include even more nodes. So we'd also have to include this one to touch the blue edges. So here the value of the min vertex cover. A min vertex cover is size 4, but a max matching was size 3. But at the very least, every single edge in the matching, we have to at least take one of the nodes touching those edges. So what else could we do? If I gave you a matching and said, can you turn it into a vertex cover, how could you do that? So in this example, we picked one node per edge, and it was almost a vertex cover, but didn't quite work out. So what if we picked both nodes per edge? Maybe that would work. So this is a really dumb algorithm. The idea is pretty much the same. We just loop through G until we run out of edges. We find any edge in G that's not covered yet, and we forcibly cover it by picking both of its endpoints. So can any edge be uncovered? No, because literally we find every single edge that's not covered yet, and we take both endpoints. So not only is it covered, it's like extra covered. So clearly this is a feasible algorithm, but it feels like it's going to take way too many nodes. It's going to pick way more nodes than we really need, right? Does everyone have that same feeling? We're kind of overdoing it here. However, it absolutely destroys the other algorithm. So these two algorithms both run in time O of v plus e. They're both linear time, depending on how you're implementing this, but you can do it in O of v plus e time. Except this one is a 2 approximation. So no matter how big your graph gets, it'll still do no worse than giving you half the optimal size. Or it's no more than twice as big as necessary. So this is probably very like, whoa, why? So let's just think about it. So let's prove it. So what do we know? So based on our theorem here, this weak duality, we know that the optimal solution is at least the size of a max matching. That's just by weak duality. If opt was ever smaller than this, it has to be missing one of those nodes, or one of those edges in the matching. So you have to at least pick one vertex per edge in a matching. But how big is our solution? We pick exactly 2 nodes per edge. So our algorithm, the size of our algorithm, is equal to 2 times the maximum matching. And since the maximum matching is at most opt, this is at most 2 times opt. That's it. So the key step here, the actual hard part, is this part, the weak duality part. But once you have that, proving it's a 2 approx is super easy. By literal definition of our algorithm, we grow a maximum matching, and then we pick both the nodes in it. So literally, by definition, the size of our vertex cover is exactly equal to 2 times the size of the maximum matching. For each edge, we take 2 nodes. And then by weak duality, MM is at most opt. And so we get this relationship. Pretty crazy, right? So here's an example where the greedy algorithm isn't horrible. It's not terrible. It's worth something. If you're in a pinch, this is useful. But if you have duality, you can make this really dumb and simple algorithm that's super fast and still gives you an incredibly good, accurate solution. So any questions on this problem?
Explain duality again.
So I explain it in depth in a video, so I won't go in depth, but the idea is a matching for any edges, E and E prime in a matching. By definition, a matching is a set of no disjoint edges. So E and E prime don't share an endpoint. So in particular, let's say it looked like this. If we had this kind of graph, you could pick just U, and that covers all the edges. But that's not a valid matching. In a matching, it would have to look like this. The 2 edges are completely separate. And so if the 2 edges are completely separate, you have to take at least one node touching both of them. So for every single edge, you need at least one equivalent node to cover it. So that's the idea. So this problem that, it's NP hard, we can't really solve it efficiently, we can really easily solve it almost correct. So in linear time, we can solve it almost exactly correct, but not exactly. But if we just made the 2 into a 1, it's instantly exponential time. And it's a completely open problem whether we can make that 2 smaller. Maybe you could make it 3 halves. Maybe you could make it 1 plus epsilon. Well, actually, we can provably not do 1 plus epsilon, but maybe you can make it smaller than 2, and we don't know. So, pretty crazy. Okay, so let's look at like the most famous NP-complete problem of all time, the traveling salesman problem. I'm sure everybody's heard of it. So, in the traveling salesman problem, you're given a graph, and we're just going to assume it's fully connected, so it looks something like this.
Can I ask a quick question?
Yes.
So how do we know that that's the maximum matching? Just by like taking.
You mean why does the algorithm make a maximum matching? So it picks at least a maximum matching. So it might pick actually more. So for every single edge in the graph, we potentially add it to the matching.
And then are you removing the vertices?
Yeah, so we're removing the vertices and all the edges that touch them. So if you had this edge u to v in your graph, in the loop, when uv shows up, what you're going to do is kill all of this. All of these edges are gone.
So can you have less than maximum matching?
Nope, it could be more than that, though.
How can you have more than a maximum?
So this will be a maximal matching because suppose we missed an edge for the sake of contradiction. In the loop, we find the edge. If there was ever an edge we missed, well, the loop is going to explicitly find it.
Well, because like I was thinking, for example, in this graph,
Mm-hmm.
if you get rid of u and v, like if this was the entirety of the graph, if you remove u and v, there's no more edges in this graph.
Yeah.
It's just one, right?
Yeah, so if you remove u and v, then you've covered everything and you're done.
But then the actual maximum is not one.
So it'd be, so this is called a maximal matching, not maximum. A maximal matching just means you can't add more edges to it. So here, if we picked uv in our matching, we can't also add, say, u to w, because they share an endpoint. A maximum matching says you pick the most edges possible. Maximal just says you can't add more to it. So a maximal matching is smaller than a maximum matching, but that just helps us, right? So this is at most a maximal matching. So this is picking a maximal matching, which is at most a maximum matching, which is at most opt, which is really confusing, which is why I kind of just skipped over it.
But then the approximation value would be like bigger.
Nope, it's always 2. It's the same proof. So do you want to make it more precise? This is equal to twice the maximal matching.
Oh, since it can only be okay.
Yeah.
Okay.
So yeah, I mean, lots of these have details I'm skipping because I just want to emphasize the idea. So for a traveling salesman problem, the idea is you have some salesman who's starting at some node S, and he wants to take a tour of all these cities, and he wants to hit every city exactly once to sell his products and then come back to his hometown. And he wants to do this as quickly as possible. So he wants to avoid taking really big edges. So here's an example. So we have some weighted graph, and we want to find a cycle that hits every single node and has minimum total length. So we just want to find a cycle that touches every node. It's also called a spanning cycle, just like a spanning tree. And that has min cost. So out of the set of cycles that touch every node, you want to find the one with minimum total cost. But I'm sure everyone's heard of this, so I'm not going into a lot of detail. So why is this NP hard? Because it's a harder version of a different NP hard problem. So Ham's cycle in the book, Ham's cycle is just the problem of finding a cycle that hits every node. So just the first requirement is already NP hard, and now we've also made it an optimization problem. So formally, to prove it's NP hard, you can use the following reduction. You just take your original graph and create the following weights for it. So we're starting from Ham's cycle, and we're reducing to traveling salesman problem. So I'm given some graph, and I'm turning it into a weighted graph with the weight function L. And here what the weight function is, it just says the length of an edge is 1 if E is an edge in the graph, and 2 otherwise. So technically this is a Kn. So the traveling salesman problem we're assuming is on complete graphs, so every edge exists between nodes. But the original Ham cycle problem doesn't have to be complete. So the way we simulate completeness is by using an appropriate length function. So if an edge is in the graph and is used, it costs 1. But if we tried to use an edge not in the graph, the original graph, we get penalized. It'll cost extra. And so if we find a traveling salesman cycle of min cost, it can never use one of these edges. Because if it ever did, we could substitute it out for a 1 edge for lower cost. So the only reason traveling salesman problem would use a 2 edge is if the original graph did not have a cycle that touched every node. On the other hand, I mean, it's an if and only if, so that's basically the reduction proof. So just to write that out, only reason TSP would use an edge not in the edges of the graph, the original, is if no Ham cycle exists. Otherwise, following a Ham cycle has cost 1 per node. And since it's a Ham cycle, it hits every node, and so it's exactly n. So if there's a Ham cycle in the original graph, the TSP instance has a TOR of cost n. But if the original graph has no Ham cycle, then the TSP TOR will have size at least n plus 1. Because one of those edges will have cost 2. In the worst case, you use only edges not in the original graph, which will have cost 2 times n. So that would be a really bad situation. But all that matters, if we use even one edge not in the graph, we get at least n plus 1 cost. So basically, the algorithm would be run TSP on a complete graph with that corresponding length function. If the solution is n, we return true. If it's bigger than n, return false. So the algorithm is run the TSP algorithm on KNL. If answer equals n, return true. else answer is at least n plus 1, return false. Clearly, this is polytime. We just can make a complete graph in at most n squared time by brute force, and the length function similarly. So it's at most n squared time or v squared time to create the new graphs, and clearly the reduction is then correct. So a neat feature of this is I picked 1 and 2 here, but you could make these any numbers. So you could make this number really big. You can make it as big as you want. Pick any function of n, and you can put that there instead of 2. So this could be huge. So, what's the takeaway here? Not only is it NP hard, but this actually proves it's hard to approximate. So for any function n, there is no f of n approximation algorithm unless p equals np. So in the previous problem, we could approximate it within a factor of 2. Pretty good. For this problem, no matter what you do, you can never approximate it, ever. For any approximation factor that's smaller than exponential, so you can approximate it like you can do f of n equals 2 to the n. That's fine. You could do that. Actually, wait, technically it's double. It's double. 2 to the n. Not important why, but to be accurate, that's what it is. So you can do a massive number, but for anything smaller than that, you can never find an approximation algorithm with that factor for the problem. So forget about a constant, right? Forget about log n. You can't even do 2 to the n. So this problem is so unbelievably hard. It's just crazy. And yet people want to solve this all the time. Like, this is a problem we see in everyday life. And yet it's just basically unsolvable. So what do we do? If the problem can't even be approximated, what should we do? I heard whispers. Who wants to say something more confidently? Yes. Don't solve it? Okay, let's make that more positive. Let's turn that into a positive statement. Okay, so we can't solve it, so let's solve something else. So if your boss asks you to solve this problem, you say, well, we can't solve it, we can't even approximate it, but here's like a slightly simpler version or a slightly tweaked version that we can solve. And most people will be like, well, it's close enough, sure. And then you can just solve that problem. So if you're a math person, that's not an option, but if you are in industry, it might be an option. So, give that a shot. So what we're going to do is we're going to solve a slightly different version of the problem called the metric TSP problem. And the key idea in this problem is we need to satisfy the triangle inequality. So if you ever have some nodes U, V, and W, it always has to be the case that the length of the edge from U to W is at most the length of any path from U to W. In particular, it has to be at most, so one example would be the length of U to V plus the length of V to W. So in other words, it's faster to take a direct route than to take an indirect route. So direct routes are always faster. So in real life, this is obviously true because physical distances they satisfy Euclidean distances, right? And we know for Euclidean distances, the distance between 2 points in the plane is at most the distance between some other point so real life, we live on a 2D Euclidean plane, so we have Euclidean distances. So for example, it's faster to go from Madison to Milwaukee than to go from Madison to Chicago to Milwaukee, obviously. And that's all this is saying. So this is not a huge restriction on the problem. It's really honestly just a slight tweak to the problem. But we're going to see this slight tweak is going to make it from being impossible to approximate to easy to approximate. And that's the crazy part. So just by adding this one physical restriction that the real world actually satisfies, will make the problem solvable. And sometimes by doing this, you even make it like actually solvable. So you can make versions of TSP that are in P. You can solve it in poly time exactly. For metric TSP, we can't solve it exactly in poly time. It's still NP hard, but we can solve it approximately. So let's think about how to do that. Any ideas? So we have this giant graph. All these edges everywhere. Yes. That's not an option. The weights are given to you. Yeah, some numbers there. Let's think. Do we know any problems from class that involve something that's close to finding a short cycle in a graph? So there's two problems we discussed in the class that are kind of like this problem. What's the most obvious one? Shortest path. So specifically, remember we can compute a single source shortest path tree. So that would look something like, starting from this node, that's the shortest path, that's the shortest path. Now, what's the issue here is, remember, the triangle inequality says the direct routes are always faster. So any shortest path tree will always look like this. It'll just be edges directly to everything else. And there's no reason why that would give us a short cycle. How do we even turn that into a cycle? It's not entirely clear. So single source shortest path doesn't seem to be helping. What's the other problem? Yep. So the other problem we talked about is minimum spanning tree. So what would that look like? Well, that looks something like 2, 3, 5. So this was a horrible example because it's going to be the same thing. We make this one bigger. Okay. So now it's going to be 10 is better. Yeah, that's a cycle. No, it's not. Oh, yeah, this 10 is better. Yeah, sorry. And then that's 7. So that's what the MST looks like in the graph. Okay, so at least it's not trivial, right? It's not some weird guaranteed shape. It could be some different shape each time. One other cool property about MSTs is we know we're getting the smallest edges. So remember, the base idea of minimum spanning trees is you're always picking the safe edges. So for any cut in the graph, you're always picking the smallest edge that crosses that cut. So basically, the individual edges are very small. So that's good. But how can we turn it into a cycle? So if I gave you a minimum spanning tree, what's the most obvious way to turn it into a cycle? Even before a cycle, let's make it a closed walk. What's a closed walk here? Say, starting at this node S. It might help if I name the vertices. So if we're starting at S, what's the next node we should go to? So like this way, you mean? Okay. Now what? Did you say 8? Oh, okay. He switched it up on me. So basically, we'll go down to W. And then we can just retrace our steps, right? So let's just go back the same way. Dang it. So we go back the same way. Now we take this part. We get stuck, so we just go back the same way. So we walk on every edge exactly 2 times. So what's the cost of this tour? So it's not a cycle yet, but let's just say, what's the cost of this specific walk? Yep. So the cost of this walk is exactly equal to 2 times the size of the minimum spanning tree. Now, how do we turn a walk into a cycle? Well, remember there was that proof that said every walk contains a path by induction. And similarly, we can say every closed walk contains a cycle by induction. So there is a cycle in there somewhere. We just have to figure out how to compute it, but it does exist. Now let's say we have computed the cycle. So we turn the walk into a cycle somehow. How big is the cost of the cycle versus the cost of the walk? Why? Yes. So the cost of the cycle is smaller than the cost of the walk, because basically what the cycle is, it's the walk, but we ignore repeated nodes. So every time we would want to repeat a node, instead we skip to the next node. So let's say our order we picked was S, U, V, W, X, Y. That's the order we hit every node in. So we're at S, we're at U, we're at V, we're at W. The next thing we want to do is go to X, but to get there we repeat nodes. So instead of doing that, just don't repeat the nodes, just skip directly to X. And because of the triangle inequality, skipping directly to X will cost less than going through this entire path to get to X. So we can just skip to X. And then once we're at Y, we skip back to S. So if you give me an ordering of this tree, we can always figure out how to turn it into a cycle by just seeing the order and skipping directly ahead by taking the edge. And this is less cost by the triangle inequality. taking the single edge from W to X is cheaper than taking a path all the way through all the other nodes to get to X. Any questions on this?
When we say skipping to X means finding the shortest path from W to X.
Nope. Generally, yes, but because it's a complete graph, the shortest path is always the edge.
Oh yeah, so you said it's a complete graph.
Yeah. So yeah, in general, you'd be finding a shortest path, but in this special kind of graph, we just need to take a single edge.
How do we come about this ordering?
That's the next step. Yes. I just picked a random S. Doesn't matter. Yeah. Because remember, we're computing a cycle. So any node on a cycle you could think of as the first node. They're all equivalent. So in particular, we can do this for any order of these nodes. As long as our order steps through each of those edges exactly twice or less, that order will work. So is there an algorithm we know that computes an ordering of nodes? What is it? Yes, I was hoping you'd say that. So topological ordering is one option if it was acyclic, which it is acyclic. The tree itself is acyclic. So you could do that. You could compute a topological order, and that totally works. What's an even easier thing you could do? How do we even find topological orders, really? Oh, you had it the first time. Depth first search. So topological order totally works, but it's overkill. So what we can do is compute the MST and then just use a depth first search on it, starting from any node you want, and that will label the nodes. So here's an example of what the algorithm looks like. First, we compute the MST. So that thing on the left, this is the MST. That's not the original graph. Remember, the original graph is complete. Then once we add the MST, we just pick a random start node, say the middle one, and then we compute a depth first search. So in this example, the depth first search starts at this node 1, goes down to node 2, backtracks back to 1, then it's going to go down to 4, down to 3, backtracks back to 4, goes to 5, etc. And it'll end up hitting every edge twice. Or you can think of it as hitting every edge once, but with a backtrack. Either one's fine. But either way, this is computing the post-ordering. So remember, for DFS, you can create a post-ordering, a pre-ordering. There's all kinds of ways to use the clock parameter. So this specifically would be a post-ordering. Not super important. Just think of this as any depth for search ordering. And now what's the actual TOR? Well, we're just going to do skips. So we go from 1 to 2, and now the next node would be to go to 3. So we labeled that 3, and so we just skip right to 3. Then the next one's 4, so we go to 4 directly. Now 5, we skip right to 5. Well, it's not even a skip, that's a direct edge. Now from 5, we skip to go to 6. We go to 7 directly, and then we skip back to 1. So we compute an MST. Compute an MST. Do a DFS to pick labels or to pick an ordering. Of the nodes. And then we follow the order and use skips if needed. That's the entire algorithm. So what's the runtime of this algorithm? What's the slowest part of the algorithm? Yep. So obviously doing a depth first search, that's linear time. Even if you modify it to do labels, following the order is literally linear time. You're touching each edge or each node once. So the hard part is computing an MST. And we know from lecture that if you use prims or kruskals or pretty much all the standard algorithms for MSTs, they take O of E log V time. And now since this is a complete graph, the number of edges is basically the number of vertices squared. So we can rewrite this as O of V squared log V. So it's pretty fast. Like, that's not bad at all. That's the same running time as if we ran Dijkstra's or did any other non-trivial operation in a graph. So that's pretty fast. But is it really a good approximation? Well, I claim it's a 2 approximation. So it's a very good approximation. So here's the proof in words that probably isn't helpful at all. So let me draw you a picture. So let's say we had some graph. And let's say this was the shortest cycle. So this is the TSP opt, is that cycle. Now notice that if we removed one edge, it's a spanning tree. So if we take this cycle and remove any edge on the cycle, it becomes a spanning tree. Everyone see why that's clear? Deleting an edge just makes a tree. And because the cycle was spanning, touching every node, the tree is also spanning. So what's the cost? The cost of the tree is equal to the cost of C minus the cost of E. And so it's smaller than the cost of C. So if you took your minimum cost TSP Tor, remove an edge, it becomes a spanning tree. And that's just one spanning tree. So in particular, that's smaller than the optimal MST. So the cost of a minimum spanning tree is smaller than cost of the specific spanning tree you get from removing an edge from your Tor. And so what do we see? Well, the cost of an MST in your graph is smaller than the optimal TSP Tor. Make sense? So to put it another way, you can think of our optimal solution as a spanning tree, and then we pick the best edge to add to it. That's what this is saying. So now what is our algorithm doing? Well, we already argued that our algorithm, the cost of our algorithm, is at most twice the cost of our minimum spanning tree. And so from that thing above, that inequality, we get it to most twice opt. So the critical idea here to prove approximation guarantees is to find a good bound on opt. So we don't know what the exact optimal value is, but we do know it's at least the size of a minimum spanning tree. And because we know that, we can incorporate that into our algorithm. So we use the lower bound on MSTs. We use MSTs in our algorithm, and so we can exploit that relationship to get a good algorithm with small cost. So we're exploiting bounds on opt in terms of structure of the graph, in this case MSTs, to get a good algorithm. And that's what we were doing in the previous problem too. we used the fact that a maximum matching is a lower bound for the min vertex cover problem, and then just incorporated matchings into our algorithm. And this is kind of the pattern for approximation algorithms. You first try to understand the problem. You try to relate it to something you know about or know how to solve. And then you incorporate that thing into your algorithm and exploit the relationships. So any questions about TSP?
In terms of the size of the cycle,
Mm-hmm.
our algo should be greater than optimum algo, right? Because we are not able to find the minimum.
Yep. So this is also smaller than, or it's, yeah, cost of opt. So opt is smaller than alg, but alg is no worse than twice of opt. Let me just say, not cost, but opt. Yeah, so since opt is the optimal TOR, it's always going to be less than or equal to whatever TOR we create. And sometimes we'll get lucky and we'll actually find the optimal TOR. But in general, that's usually going to be a strict inequality.
So this only works when everything's connected to each other and the fact that going directly is faster than.
Yes. So the fact that it's a complete graph is not important. Instead of skipping being a single edge, skipping will just be the shortest path. So that's, you can change that assumption. But the triangle inequality assumption is critical. If you change that, it's instantly inapproximable. So this is the key part, is the triangle inequality. It says that the length of the edge from U to W is always smaller than the length of U to V plus the length of V to W. So taking the direct route from U to W is always faster than taking some other route.
Oh, so like the direct route is not the shortest.
Yeah. So going directly from Milwaukee is faster than going to Chicago and back to Milwaukee. Yeah.
So you explained it that after doing the MST, we just loop over the MST, right?
We do a DFS on it.
Yeah, but earlier the example that you've shown, you were like kind of looping around the MST, right?
Yeah, so that's just to give you the idea that we create a closed walk that just repeats edges twice. And then the actual thing we create, the cycle, will be smaller than that. And that thing is obviously twice the size of the MST.
That's also just like running DFS. And that's why we say even like DFS will give you less than twice of MST. How do we infer that it gives us less than twice of MST?
So any closed walk will be twice the MST, any of them. I just gave a specific one. So any cycle will be at most any closed walk, because a cycle is a minimal closed walk.
How does the same thing comes up in when we basically run DFS on MST?
So DFS gives us an ordering of the nodes, like this. It doesn't matter what ordering of the nodes it is, just any ordering. So DFS just gives us some ordering, and then given an ordering, we just apply the skips. So every time this isn't a direct edge, because we have to repeat something, we use the skip edge instead.
Yeah, but we are running DFS on MST.
Yeah.
So how does the factor of 2 comes in when I'm running DFS on MST?
The DFS part isn't important. The DFS just gives us a specific ordering. Yeah. The general argument is just given an ordering, we can create a cycle. A cycle is the most a closed walk, and a closed walk we know is exactly equal to twice the MST.
Yeah, but the ordering of DFS should be equal to MST, not twice MST, right? Because there's no closed walk that's coming into the picture there.
It's smaller than the closed walk. It's a cycle. So if you're saying like a DFS itself, it touches every edge once, so it's exactly the MST, that's true. But the issue is that's not a cycle. that's just repeating the tree again. To make it into a cycle, we have to physically follow the edges, and so we'll end up repeating nodes. Yeah. Yes, the cost of the cycle is at most the cost of the walk, which is equal to twice the MST. Yeah.
And then when you're doing skips, you're always taking a route that is shorter than taking the enclosed walk.
Yeah.
That's why it needs to be smaller.
Yeah, so this is a way to create a specific cycle from a walk. That's what this is. So this is really a walk. Implicitly, it's assuming you're revisiting nodes as necessary. And I'm just saying instead of revisiting nodes, just don't. Just don't revisit nodes. And so this gives us a cycle. And a cycle is at most the same walk. And so we get that relationship. So there's a lot of intermediate steps here. But let's move on to the last example, because we're going to use DP again. Yay. So this is the knapsack problem. It's pretty straightforward. It's a problem we've kind of done in the homework implicitly. It's just the problem of I give you a bunch of items, 1 through n, and each item has a weight, W1 through Wn, a weight budget, B, a reward, R1 through Rn, and the goal is to pick items so that reward is maximized. So for each I we pick, the reward of I is maximized, but the total weights we pick is at most our budget B. So you could think of this as your packing luggage, and there's certain items you really want to bring, but obviously your luggage has a limited capacity, so you're trying to stuff as much as you can in your luggage to maximize your reward. So it's very similar to the greedy algorithms we've seen before, like file sorting or like course scheduling, where you could have tried to pack as many courses as possible, subject to some constraint on conflicts. So this one's even more physically intuitive. You have basically a backpack, and you want to bring all your favorite stuff in there, like maybe your favorite book, maybe an apple, maybe some cookies, whatever. But you have a limited amount of stuff you can put in your backpack, and each thing has a different reward. So obviously the cookie is going to be the highest reward. It's amazing. Maybe you don't really care about the apple as much, but if it fits, you might as well add it. You're still getting something. So that's the problem. Maximize your reward while making sure you don't go over your budget. So any questions on what the problem is? Okay, so the decision version of the problem says, can you achieve at least a certain amount of reward? So the decision version says, can you get at least R total reward? So how do we reduce subset sum to this to prove it's NP hard? Well, remember in subset sum, we want to pick elements that sum up to a target t. And now notice here, we want to have a sum of things be at most b, and a sum of things being at least r. So we could just make both of those t, and then that would tell us we can get a sum of things that is at most t and at least t, so it equals t. So what's the reduction? We're going to take our s and t and create the weights. So wi equals the reward of I equals the ith thing in the set. So we make the weights and the rewards the same, and they'll always be the ith element of our set S. Then we're going to make b equal to r equal to t. So now if there exists a subset that sums to t, then, so let's say the subset is A, has the sum of all I in A of Si. So let me make this specifically in indices. So we're going to focus on the indices of the items. So this equals to t. Well, that means, the sum of all I in A of the weights, well, that's literally by definition this, so equals t, which is equal to b. So we're fitting within our budget. And similarly, the sum of all I in A of the rewards, well, that's equal to the sum of I in A of Si. That's equal to t, which is equal to r. And so, in particular, it's at most b and at least r. And so the next problem is a yes instance. On the other hand, if the next problem was a yes instance, well, we know this is true, and so we found a subset that sums to t. So this happens if and only if this happens. So that's why the reduction is correct. Obviously, it's not only poly time, it's linear time, because we're just copying S to the input as knapsack. So that's the high-level sketch of the reduction. This is the exact reduction, but this is why it's correct. That's the idea. Yes?
I may have gotten mixed up with all of it, but B is the budget, which in my head is the amount of items that you can have in the bag.
Yeah.
And the reward is essentially the cost, or basically the reward. So the reward and the budget could be different, right? In this instance, it could be 3, but the total reward of those 3 items could be like 10, for instance. So how could they be the same? Or how could they equal?
Are those two sums equal?
So SI in this respect is the reward, correct?
And it's also the weight. It's a good point. To prove the converse, well, what if the weights was strictly less than b, but the rewards were strictly greater than r? So you can't conclude the sum's equal to t. But that's impossible because those are exactly the same sum. So if one of them is smaller than b, which is t, and the other one's strictly greater than, well, then those sums aren't equal. That was a contradiction. So let me so if this thing was strictly less than b, but we know by definition this is equal to t, which is equal to b. So we would have, this is strictly less than b, which is t. This is strictly greater than r, which equals t. And so this sum is simultaneously less than t and greater than t. But it's the same sum. How can a single sum be greater than 5 and also less than 5 at the same time? You can't. So that's the key. The important part is that they're exactly the same numbers. That's why it works. Any other questions about this?
Actually, like, really lost. So you're forcing every weight the reward to be equal, or?
Yep.
Okay.
So we're defining the weights to be SI, and we're defining the rewards to be SI.
Okay.
Remember, we're solving subset sum using the knapsack algorithm as a black box. So we're creating an input to the knapsack problem. And this is the specific input to the knapsack problem we're going to pick.
Oh, so we're solving the subset subproblem using that.
Right.
Yeah.
Yeah.
Okay, so the knapsack algorithm can have different stuff, but the subset sum doesn't because.
That's just how it's defined. So in particular, you could think of subset sum as like a special case of knapsack. That's why the reduction's so straightforward. So knapsack is a harder problem than subset sum, and so it's NP hard. But I claim we can solve knapsack using dynamic programming, which shouldn't be too surprising because we solved subset sum using dynamic programming way back in chapter 3. But technically, remember, it's pseudo-polytime. It's not actually polytime. So there is a drawback, but we're going to fix the drawback. So how can we solve this with DP? So there's one really straightforward way to do it, which I'll leave you guys to think about. But to make this work, we have to do a really weird DP. So I'm just going to kind of tell you what it is. So we're going to do min weight of I V. This is going to be the minimum weight possible to fill a knapsack using items I through N and achieving value at least V. So the most natural way to do it, I think, would be to do the opposite, which is what's the max reward you could get subject to your weight being at most some W, right? That's kind of the most natural thing to do, and you can do that. And you'll get a similar algorithm that runs in O of n times B, because B is the highest budget. Now, there's a special reason I'm doing it this way, which we're going to see. And this way is going to be O of n times V, where capital V is the total reward. So V is equal to the sum of all I equals 1 to n of the reward of I. So V is the max possible reward we could get. But we're going to do it this way. So if we do it this way, which is admittedly weird, our return is going to be weird. So what's our final return? We're given a list of the items in order. Yeah. So for sure, we're going to be putting a 1 there because we're going to consider all items. But what should that second parameter be? Yes. Do we want to achieve 0 value? What if we can't achieve capital V value? So I want this to be a solution to the original knapsack problem. So remember, the knapsack problem says, given a constraint of B on your weight, what's the max value you can get? It's weird. It is weird. We're going to return the most value, the max V possible, of so we want to find the V for which, the largest V for which max weight is still at most B. So specifically, this is going to be a predicate. It's going to be true or false. So we're going to find the maximum V for which this thing is true. So why is this a solution to the original problem? Well, we can't let our budget, our total weight, to be at most B. And we know MW is the minimum weight, right? So if the minimum weight possible is less than or equal to B, we know it's a feasible solution. We can pack all that stuff into the knapsack. And so we keep trying bigger and bigger V until this is no longer true. So at some point, there's no way to actually achieve value V without going over budget. So that's why this algorithm works. Now, if you did it the other way, it's way more straightforward. You just say return, exactly MW of 1B, and you're done. Really easy. This one's a little more complicated, but there's a benefit. So first, obviously, let's solve it. So what's the recurrence going to look like? So like obviously, let's say I is greater than N. Can we achieve value V? What's the min weight possible? So this is going to be infinity. There's no weight possible to achieve value V. So you could also think of this as like a true-false if you want. Unless V is 0. So if V is 0, then you can do it using 0 weight. Otherwise, it's infinity. So 0 if I is greater than N and V equals 0. So those are our base cases. If we have no items left, the only value we can achieve is value 0, and the weight of that solution is also 0, because empty knapsack is weightless. So on the other hand, what do we do? What's the decision we have to make at step I? Yep, so we can either put item I in the knapsack or not. So what are the two cases? Well, we have a min of, if we put it in, we get the weight of I plus the min weight of I plus 1. And then what's the new value? Opposite. It's V minus the reward of I. So remember, in total, we want to achieve V. So if we use I, we now need to achieve V minus Ri. So this is for the same reason as we did with subset sum. Otherwise, it's just min weight of I plus 1 and the same V. Okay? So that's the DP recurrence. That's the final return. I guess just to give you a quick sketch of what the table will look like, it's going to be we have I and V. Each I depends on lower I and lower values of V, or the same. So we either have I plus 1 same V, or I plus 1 and a smaller value of V. You know, maybe any possible one, it doesn't matter. So these are the ones that IV depend on. And so the eval order is going to be, we need I starting at n and going up. So this is n, this is 1, plus 1 to be really precise. And then V, it's going to start at capital V and go down to 0. And we want those to be going in this direction. Strictly speaking, it actually doesn't matter. Once we've evaluated the bottom row, we've evaluated all of them anyway. But that's the most natural order for V, is to go from 0 and up. So working out those DP muscles again. So like I said, what's the running time going to be? Well, clearly it's O of n times V, right? So there's n possible values of I, there's capital V possible values of V, and we just do a constant time min for each subproblem, so that's the total runtime. And this is pseudo-poly time. It's not efficient, but we can fix it with rounding. So the idea here is if V is small, then it is efficient. So as long as we can guarantee the maximum possible value is small, then we can just use this algorithm and it's fine. So what we'll do is we'll just round every possible reward. We'll round the rewards so that the V is small, and then just run that original algorithm. So the idea here is if we round them down to a smaller V, then hopefully we won't lose too much during the process. It's not going to be exactly correct anymore, but it should be close. That's the hope. So the first thing we do is we define alpha to be n, the total number of items, divided by the maximum original reward, and this epsilon parameter, which is how we pick the accuracy. Smaller epsilon means higher accuracy. And then the rounding is going to be scale vi by alpha, and then turn it into an integer by taking the floor. And then we solve this new version of knapsack with the rounded rewards using this algorithm. So first, for the runtime, how big is V prime? Well, V prime is at most n times the maximum value in there. And what's the maximal value? Well, it's going to be alpha times the original max. So what's that? Well, alpha times the original max is just n over epsilon. So this is equal to n over epsilon, which equals n squared over epsilon. So the total running time is going to be O of n cubed over epsilon. So it's polynomial time. So any questions on why V prime is bounded in that way? The sum of rewards is at most n times the maximum reward. And then I'm just using the fact that we defined alpha based off of the maximum reward, and so it simplifies nicely. The V maxes cancel. So this whole thing is V prime max. Okay? So the critical idea is we're just rounding our numbers and then using the DP algorithm. And another observation here, notice the optimal for the new instance, the prime instance, is at most n squared epsilon, And that's just because the maximal value even possible is at most n squared over epsilon, right? We can never do better than taking everything. It's also at least n over epsilon, because any optimal can at least just take the biggest one. So op prime can at least take v prime max, the biggest item. Or I should say the biggest reward item. So at the very best, we can get n squared over epsilon, and at the worst, we can at least take that single item, which is n over epsilon. Okay? So now here's a lemma here that I won't go through in intense detail, but we can bound the rounding error. So if we define the value of a subset of items to be just the sum of all their values, and we also have v prime is the subset of all the values in the rounded instance, then you can prove that the value of the rounded instance is no more than alpha times the original value, and it's at least as large as alpha times the original minus the size of the number of items. So the idea here is, at worst, you're getting penalized 1 for every single item in your set, which makes sense because you're rounding each number in the set. And so each one at worst was 1 off from, maybe you should have rounded it up instead of down, so you're getting a rounding error of 1. And in particular, from that equation here, we know that opt prime, n is at most epsilon times opt prime. And so the size of S is at most n, which is at most epsilon times opt prime. And that's for any S. And so you can plug this into this equation, and what's going to happen is this. So A is the solution to the rounded instance. And A star is the solution to the true instance. Then what do we know? The value of A is at least v prime times the same A, and that's just by definition of the rounding. We get a factor of 1 over alpha times v prime. Remember, because v prime is exactly v times alpha, so we're just dividing by both sides. Now, because A is the optimal solution to v prime, this is at least the solution A star of v prime. So the true solution for the original problem is also a solution to the rounded problem, but it's not necessarily optimal, and so it could have smaller value. Okay? Then we apply the lemma to A star. So this is the lemma. This is because A is optimal for the prime instance. This is just algebra. And then this is where we use those bounds. So this is the optimal solution for the original instance. And so this thing is exactly opt. And V max, this is a lower bound on opt. And so we get opt minus epsilon opt, which is equal to 1 minus epsilon opt. So instead of getting half of the possible reward, we can get 1 minus epsilon for any epsilon. So in particular, if you put in 0 for epsilon, you're getting the exact solution. But in general, you're going to have a smaller epsilon so that your runtime is smaller, or a bigger epsilon so your runtime is smaller. And this is called a fully polynomial time approximation scheme. This is basically the best we can do in approximation algorithms. In polynomial time, we can get as close to a solution as you want. So for all intents and purposes, it's basically a solvable problem, right? Your employer's not going to really need you to be 100% accurate. They'll be okay with like 99%. Like there's not a huge difference there. So this is basically the pinnacle of the course, and it's done with DP. And that's it.